Hello, Chem 112 students. Here's your video on using the Nernst equation. The Nernst equation is used when you need to calculate the cell potential of a non-standard cell, when it's got a temperature or some concentrations that are different from ideal conditions. This is what it looks like. Let's walk through its anatomy step by step. E cell is the non-standard cell potential. It's what you're trying to solve for. It lacks that little zero to tell you that it's non-standard. E0 cell is the standard cell potential in volts, and you get this from combining standard reduction potentials. This here is the Nernst constant. This form of it takes into account temperature, gas constant, and Faraday constant effects. This N is the same N we've been working with. It's the number of electrons transferred in the overall cell reaction. So you determine this by balancing the half reactions and looking at the coefficient in front of the electrons. Lastly, you have the log Q. Q is the reaction quotient. This is the mass action expression for the overall cell reaction, just calculated with the non-standard concentrations. Now, how do you use this whole big equation? Well, first, obtain the half reactions and the overall reaction for the cell. This will let you obtain N and the standard reduction potentials. You'll calculate your E0 cell from those standard reduction potentials using the E reduction minus E oxidation. Number 3, you'll write the mass action expression for the overall reaction and calculate Q. And then the last step is to plug everything into the Nernst equation and solve. Let's see this in action. Calculate the cell potential at 25 degrees Celsius when H plus concentration is 1 molar, zinc 2 plus concentration is 0.0010 molar, and the partial pressure of hydrogen is 0.10 atmospheres for this galvanic cell. Now you should recognize both of your half reactions here. We've got zinc being oxidized to zinc 2 plus. That's one of the ones you'll find on your table of standard reduction potentials. And also we've got this 2H plus becoming H2. This is the standard hydrogen electrode, the She. So step 1, obtain our half reactions and our N. Pulling them from the table, we've got our zinc 2 plus combining with 2 electrons to make zinc 0. The potential of that is minus 0.76 volts. Then that of the standard hydrogen electrode is 0 volts. That's our designated 0 point. Note that we're using 2 electrons as reactant. In both of these are balanced, N equals 2. Next, we need to calculate E0 cell. Our reduction process is the standard hydrogen electrode. So that's going to be our 0 point, and then we're going to subtract the oxidation process potential, giving us an overall cell, standard cell potential of 0.76 volts. Next, we need to write the MAE and calculate Q. Q, just like K, will equal the molarity of zinc 2 plus times the partial pressure of H2 over the concentration of hydrogen ions squared. Remember, it's products over reactants. We can use both molarities and partial pressures of gases in our mass action expressions. And then the zinc here doesn't show up because it's a solid. We plug in the concentrations the problem gives us, crunch those numbers down, and we get 0.00010, or 1 times 10 to the minus 4. Last, all we have to do is plug this into the Nernst equation and crunch our numbers. So E cell is going to equal 0.76 minus 0.0592 over 2 times the log of 0.00010. That gives us 0.76 plus 0.12, or a non-standard cell potential of 0.88 volts. So there you go. That's the Nernst equation, and I will see you guys in class tomorrow.